Okay, so I think we can start. Do you agree, Muna? Can we start? Then we will do a little recap of what we did before, and then we will go ahead with the this second part of the training of today.
Yes, we can start, I think.
Okay, so Federica, you can go with the presentation. Thank you.
Okay, good afternoon, everyone. And first of all, thank you for participating for the session of this morning. Now we are going on with the second part. Let me share the screen and let's go back to the presentation. And if you have any question about the things we have seen this morning, please tell me. Or otherwise, I just do a little recap of what we were saying just before the break. We were talking about the math functions that are available in DSS-Vue program, which are some really useful tools which let the user to do a lot of different operations with the data set. They are subdivided into 6 categories: the arithmetic, general, time function, hydrologic, smoothing, and statistics. We have already seen some examples from the arithmetic functions, which let you to do some arithmetic operations, like we saw an example about adding a constant value to a selected record. And we have seen the general functions, which include various operations. Then we were analyzing the time functions, which let you to do some modification and editing the time characteristics of your data set. We have done one exercise about the accumulation over a period. We started from a record of precipitation with the 1 day time step, and we did an accumulation over 1 month and over 1 year. So now let's try to do another small exercise about the time function. This time we will try to do a shift in time. This function let you shift the times in time series dataset by a specified increment or to start with a specified date and time. So to do this example, let's select one of the record. I select, for example, a precipitation of the Luna-Elso basin. I click the math function button from the toolbar. Then I move to time function in this 6 tab on top of the window. I keep the minimum, maximum. No, sorry. From the operator menu, I change in shift in time. And in this case, when you select this math function, you have to insert some values. You can specify the amount of time to shift by the dataset you have selected, or otherwise you can select to shift the whole dataset in order to make it starting in a specified date and time. So you can change the first date and time of the whole record, and then automatically the entire records will be shifted to and adjusted to this new date and time. Let's try to shift by amount. So for example, let's try to shift the data set of 3 days. If you type 3 in this cell, you have to specify date and units. If you compute a Windows, will say to you that these shifting times will overwrite the original one, or otherwise you can select save as, and so you're going to keep both the original one and the shifted one. In this case, I select save as, and I modify the part F with shifted. So then I will be able to recognize this new data set. So let's check. This is the shifted with 1 day time step. It's the one I just modified, while this one with the 1 day time step, it was the original one. If you plot the two data sets and maybe we do a zoom in a specific month, you see that the blue one is the original one, while this one, the light blue, is the shifted, and is exactly shifted by 3 days. Every record have been shifted 3 days worth. And so these were some of the example of the operation that can be done with the time functions. Then let's see the statistics function. Or if you select the statistics tab in the math function window, you will see the following function: the basic, the linear regressions, the cyclic analysis, duration analysis, and frequency plot. These are some statistics operation that can be done with the dataset. As the other function, you have to select one or more record. Open the math function menu, select the one you want to use, and then input the required values. Click compute, and you can see the results. Let's select one of the records. I open the math function menu. I go to statistics, and automatically it will select the basic one. In this case, this function computes some of the basic statistical values for both a regular or irregular interval time series dataset. So you will be able to see some statistical and informational values like the number of valued values, the number of missing values, the last valid values with its date and time, the minimum value specified with its date and time, the mean value of all the value present in the record, the maximum value and its date and time. Then you can see also the accumulated amount, the standard deviation, the skew coefficient, the data type, and the units. So a lot of statistic information that will be automatically generated if you select the basic function from the statistics. Then the other function can be, some of them are quite specific and maybe not so useful. For example, for the data set that maybe we are going to use for also the project, but I would like to show you the cyclic analysis, which can be quite useful. So let's select this one. If you compute using this statistic function, the function will derive a set of cyclic analysis from the data set. So if you click compute, a list of new data sets will be displayed in the window, and you can select one of them and save in your path name list. For example, between these all these data set derivates by the cyclic analysis, one useful could be the redshift inch average, which is essentially an average computed cyclically in the time series. It's in this case, this function is really useful. For example, if you select a record with the time step of 1 month. So, for example, just before we did an accumulation over 1 month, I have this one. It's a time series with 1 month time step. So we have one value for each month for the whole years recorded. If you select the mapped function for this one, if you go to statistics and cyclic analysis and compute, you can select this result, the dataset results called with the precip inch average. And if you select this one and click the button Save As, you can save these results from the cyclic analysis. And now let's see what is the results of this. When you do this operation, sometimes the path name list it's not still updated, so you can go to display and to the view menu and click refresh catalog. So in this case, cannot see it. Let's put a filter. Did the operation with a blue line. Maybe it does not work. Okay, let's do it again. Select the time series with the 1 month time step. I click the math function button. Then I move to the statistic tab. I select cyclic analysis. I compute. Okay. Then I select the fourth row, the redshift inch average, which is a record that calculates the average value over a period, over a month in a cyclic way. Then I save as. Okay. Now I should have done the computation. From the view menu, I refresh the catalog. It is still not working. Okay, sorry, because I have the filter in the part C equal to precip inch, but in this case the data set as in the part C precip inch average, so I was not able to see it just because I have a filter that remove it from my list. So now I can see this this new data set, and I'll show you both in the presentation. This is an example of the results. Now I've done it with a different time series. So let's see what is the result of this cyclic analysis. In this case, the obtained record represents the monthly precipitation of an average year. So essentially, the dataset or the original dataset had one value for every month for the time range, which was about 50 years. With this cyclic analysis, the program performed an average of the value for each month. So, for example, the value in January is the average of all the values of January through all the years of the records. And this is for all the months of the year. So maybe this is an example of an average year. So you can see, for example, that the month in which it rains the most are these 2 months. Or let's see, the most rainy month are the one between June and September, which have the most high value. While in the month of December and January, they are like the dry period for these rain stations, and it rains very few during this month in average. And this is quite useful information to understand maybe the rainy season, the dry season of a station in an area you are studying. So this is almost all the most important math function for now. If you have any question, please stop me and ask it. And then we will move to an exercise which includes most of the option and operation we have seen during this day and also yesterday. Okay, if everything is clear, I just move to the new presentation. Okay, for this exercise, essentially with this exercise, we are going to demonstrate some typical mathematical operation that can be done with the DSS-Vue. For computing some reservoir inflow from gauged outflow and elevation data. It will be subdivided into 2 phases. In the first one, I'm gonna show you how to do some data screening and estimating operations, while in the second phase, we are going to see how to normalize data. To do this exercise, you will need to open the file called math function 1.2 that was present in the folder that you received in the previous email. So I will open it too. You will find this file in the folder called exercise day 2. Inside this one, there is this DSS file called math function 1.2. You can open it, and you can see there are some records of elevation, of flow, precipitation. There is also a pair data which connect elevation and storage for location. And now we are going to see something about it. These datasets and calculation are based on the gauges and the computational procedures used in support of regulation of the Corps Lake Winnebago project, which is a shallow glacially formed lake that covers approximately 214 square miles, located in the east central Wisconsin. As you can see from this image, there is the city of Fond du Lac, which is located at the south part of this lake. Then there is Jefferson Park, which is located in the north of this lake. And here from the Jefferson Park, the lake flows out to form the Fox River, and there is a gauge located a couple of miles downstream here at Lutz Park that provides some real-time outflows for the Fox River. Then the Fox River heads northeast and until it empties into the Lake Michigan, which at the Green Bay. You can see here from the right picture in the slide. And so we are going to do some operation about data recorded in this station about the lake and the Fox River. In the first part, we are going to see how to do some data screening and estimating operations. You can have some data sets which contain some erroneous values, which must be corrected before doing any mathematical operation. And the DSS-Vue software provides some criteria to screen and declare some value missing or decide to discard or change them. And so in this exercise, we are going to see 3 of the 4 mechanisms available to identify and replace some invalid data. So there is the screen using minimum and maximum, the screening with the forward moving average. Then it's possible to do also some manual editing of the values from the tabulation window. And it is possible to estimate some missing values. So there are also some math function, new math function that we are going to see in detail. So let's open the DSS file I mentioned before, the one called math function that you can find in the folder exercise day 2. I already opened it, so I just keep both the DSS and the presentation in the screen. And make sure you have selected the condensed catalog view. If you remember from yesterday in view, there are these 3 view that you can select. Select the condensed catalog. So the visualization is this one with the part A, B, C, D, E, and F all separated in different columns. And also under the view menu, make sure that the unit system and also the time zone are checked as stored, because this is an example using some English units, and so in this way we are sure that the mathematical operations will be done in a correct way with the correct units. Now select the data named Fox River Lutz Park. It's the first one. It's a record of the flow for the Fox River with a 15 minutes time step. Try to tabulate this record. And as you can see, it's this record is quite irregular. There are some missing value in the middle, and there are also many downward spikes, which are probably not corrected. This is because the station that record this flow was very old, was produced by a very old acoustic velocimeter, which made each minute an instantaneous measurement of the mean velocity, and then he multiplied it by the cross-sectional area to calculate the flow. And then with some mathematical procedures, it compute the estimating of the flow. But as you can see, these values, these downward spikes are not realistic. Probably they comes from some erroneous mesurations. And so we can use some of DSS-Vue tools to make this data set better and ready to do some further mathematical operations. What we can do is select this data set, open the math function menu, and from the general tab, there are some functions, the screen with forward moving average that we haven't seen yet, but which operates a screening of the values according to some parameters which can be inserted in the window. So let's open the math function menu. Let's click General tab, and then screen using with the forward moving average. Here we can specify that maybe the most the biggest changing in an hour for this the flow of this river can be 500 cubic feet per second, and if in the data set there is a bigger changing, this value will be rejected and cancelled from the data set. So if we put in number to average over like 4, because the data set have a 15 minutes time step. So if we consider 4 time step, it's equal to consider 1 hour. And we put 500 as a change value limit. So this is the maximum change admitted with the screen operation. And flag the true option. So all the invalid values will be set as missing. And for the quality flags, we keep the rejected. Let's compute it. Then we can plot and tabulate the computed data to see what changed. So from the math function menu, you can click the plot button. And this is the results. As you can see, many of the downward spikes has been removed. But it's useful to see also the comparison with the original one. And to do this from the display, you can check this option, original data with computed. So now when you plot, you will be able to see both the original one and the screened one. So in the legend, you see there are 2 data sets plotted, but the red one is the original one, which is visible, while the green one, which is the modified one, now is not visible. So one question is if the original curve covers up the modified one in the plot, how can you switch the order so that the revised curve is plotted on top of the original, because now we are not able to see actually what we modified. To do this, there is an option. You have to go to Edit menu, and under the plot properties, you can change here from the curves menu. With this arrow, you can switch the order of the curve. So I switch down this one. Can click apply. Okay, now you see that the modified one appears on the top, and so it's visible, and you can easily have a comparison between the original one and the modified one. Okay, this works. So you see that many of these downward peaks have been removed, not yet all of them. So for example, this one is still present, or maybe also this value seems quite not realistic, and maybe you want to remove it. But before trying to do other tests, let's also tabulate the results. If you open the tabulate, we still have the option. We see both the original one, which is the column on the left, and the modified one, which is the third column. From the tabulated view, you can select in the view menu quality. Now is set as none, but you can switch into as a symbol, and in this way you will be able to see which modification has been done from the original one to the modified one. So for example, if you see a letter R in a cell, you will know that the original value has been rejected, and in fact in the modified one it's the cell is clear, there is no value. While if you see the letter M, it means that in the original data the value was missing, and so also in the modified one the value will not be present. While if the cell of the quality is empty, it means that the original value was okay, and so the modified one it's exactly the same. Another option, which is pretty similar in the quality, you can also put this as X. There is a different code, but with the same meaning. I just explain you. So now let's remove it. And let's have a look again to the plot. Again, the modified one is below the original one. So from the edit menu in plot properties, you can change the visualization order using this arrow. So I move down this one. I apply the changing. Okay. So this modified dataset is still not really the correct one, let's say. So maybe we can try with a more aggressive screening test to try to remove, for example, these downwards peaks, this one. So let's go back to the math function view. From here, from the edit menu, we can cancel the modify we have done until now, clicking on restore original data. Now, if you plot, you see there is only the original dataset and not the modified anymore. We are still in the correct function operation, the screen with forward moving average. Let's try this time to set the change value limit into 200, sorry. And this will be a more strict operation of screening. Let's click compute and plot again to see if now the dataset has improved or not. Again, I will change the order of view for the two datasets. So I move down this one. I apply the changing. And let's have a look to this new dataset. Do you think that this stricter test has rejected any additional invalid data than before? Okay, for example, we can see that the point here around the center of the data has been removed, and also the downwards peaks that before was still present, like here and here, have been removed. So yeah, the screening has removed more invalid data. But at the same time, I was sure that this operation did not reject any of the good data. Yes, because some steep sudden changes have been removed due to this screening. So, for example, this quite fast changing has been removed. So this one, but probably they were good values in the record. So this kind of math function probably for this case is not the best option. So we can try to use another one. So let's close this math function. Before from edit, let's restore the original data. So just to verify, I plot again. Okay, I see there is only the original dataset. And let's try with another math function, still in the general tab, but this time for from the operator menu, let's choose screen using minimum and maximum. So in this case, this screen operation will remove from dataset all the values which are below a minimum value that we can set, and all the value above a value we can set with a change value limit as before. So a maximum change between one value and the next one. If we plot the data, we see that a minimum value to be set can be something about 2,200. So this is going to keep all the values above this, while a maximum value limit can be 6,000. So let's put this value in the tab, 2,200 and 6,000 for the maximum. Can keep 400 as before for the change value limit. And let's compute. I close this plot and I plot a new one displaying also the original data we computed. So check, sorry, when you go, yeah, when you scroll the mouse above the help button, it will automatically open an online page with open in the section you were using. This can be quite useful because here you can have a little manual about this topic. Okay, but go back to the exercise. Let's plot. Again, the modified is always just below the original one. So move from the plot properties, you can choose the order of the time series. Okay, and this is the result. As you can see, all the spikes, downward spikes have been removed, but there are all these values that with the screening with average have been removed before. So do you think that now the revised data set look ready for use it in other computations? Not yet. Yes, this data set is for sure better than the original one, but generally the calculation and models require all the value to be present, while in this data set there are still some missing values. So all the missing value will need to be addressed in some way, and we can notice that there is still an upward spike on the 9th of October. You can zoom in this one, which is a value that probably is not correct, and maybe we want to remove this one as well. And also, if you zoom out with the right click on the 25th of October, you see there is this strange changing in the flow values. So before addressing all the missing value, we want also to change these two little things in the data set. So let's save this screen dataset. We just save as, clicking this button, and we can specify in the part F, we can add the suffix rev, which stands for revised. Confirm. Okay, and now we have in our path name list both the original one and the revised one. Okay, now we want to remove the two interval I just show you from the main DSS-Vue screen. Clear any previously selected path name and tabulate this one. From the tabulation window, we want to enable to edit some single values here. So we have to go to edit and click the allow editing. In this way, the first two columns turn into a gray color, which means they cannot be modified. But now we are able to modify the column with the records. And we want to remove the two rows, which were the two values on the 9th of October, which sounds strange in the data set. So we can scroll down and reach that data and time. So the 9th of October, and we want to remove the values at time 7 and 3 minutes. This one and the next one, 7:18 minutes. So I select the two cells. I right click and click clear, or otherwise I select these two cells and then from edit I can delete rows. Okay. Now I can save this dataset without the two values. And I can close the tabulation window. So let's plot the original one with the revised one. I select the two rows of the two-time dataset. I plot them, and you see that we removed these two values. The red one is the revised dataset, in which we have just deleted these two values. Okay. Next step is to remove the spike down in October 25. So this one is a strange behavior of the flow in this time interval. To do this, we can set a time window. You have seen yesterday that from the bottom in the bottom part of DSS general view, you can click set time window, and you can set a specific time window. In this case, we want to set a time windows starting from 25 October of 2000 at time 00 to the 25 October 2000 at 23. We confirm this specific time window. Now, if you plot or tabulate, you will see only this specific time interval. And also, if you do some math operation, the result of this math operation are confined to this set time window. So let's go. Okay, so let's go to the math function window. Sorry, let's select only the path name of the record called revised, which is the one we are working on, the one we are modifying. So select just the dataset of Lutzpark, Fox River, which has in the part F the suffix rev. Open the math function menu. Click on the General tab and select from the operator menu the screening using minimum and maximum. So we can set a minimum and maximum value. In this case, let's plot to understand which can be a suitable value. So in this case, it's enough if we just put a minimum value like 4,500, which is this, and the math function will remove all the values below this value. So let's let's write in the minimum value limit 4,500. Let's compute. I'll close this plot. I select from display. I turn on the option original data with computed. So when I plot, I can see both the original dataset and the revised one. Now it's not visible, but if you go to Edit menu, Plot Properties, you can change the order of the time series using this arrow to move up or down the curve. Just move down the first one. Okay. And as you can see now, for the modified dataset, which is the green one, you see we do not have anymore this all the values below the minimum limit we set. Okay, let's save this new dataset with the save command. Close the math function menu and clear also the time window. So click on the set time window button in the bottom part of the DSS general window. Click on no time window. Okay, and now let's plot to see if the mathematical operation was just applied in that set time window. Okay, as you can see, there are still the values below the 4,500 in the rest of the time series. And so the math function operated only in the set time window. Now close your plot and so this can be our final data set. Actually, in the DSS file, there is one record of the Fox River load spark. You can recognize it for the part F. It's written fixed. This is a time series revised. No, sorry, we need still to fix all the missing values. So select the revised time series. To estimate all the missing value, there is a math function. You can go again to the math function menu in General tab and select the estimate missing values. This math function let you to do an estimation of every missing value. You can just specify the maximum consecutive number of missing values. So we want to estimate the missing values only if these missing values are consecutive for less than 1 day. So the time step of this dataset is 15 minutes. So if we put 97, we know that this mathematical function will be applied only if the missing values are less than a complete day. If we compute, we can see, plotting the time series, that now there are no missing values. All the missing data has been interpolated. There are no downward spikes, and maybe this can be a data set suitable for other mathematical operation that can be done. Let's save this one. Okay. I close the math windows. And so, yeah, this is the results we have already seen. We have estimated the missing values. So now we have a value for each time step. And now I would like to show you there is a record already existing in the record for the Lutzpark Fox River, which is named in the part F as USGS-CEST fixed. This is like a fixed version which has been provided by an experienced professional which have already fixed this record. And let's compare this record with the one we have revised. So select both the fixed and the revised one. Let's plot. And we can see that in the fixed one, which is the green curve, there is these downward spikes on the 25 October that we removed because these were actually some real values because of some operation that have been done near the station. So we removed it and it was not necessary. And another difference is that the fixed one have a type which is the instval, because if you tabulate, it's clear that the fixed one has a type instval, while the revised one that we did have a type of per average, period average. So what does redefining this parameter type to instval actually change anything? What is the difference between instval and per average? Yesterday you say something about these two type, and the difference is the meaning of the time step, because if we consider let's have a little zoom on it. For example, here, or the image in the presentation, the per hour, which stands for period average, set an average value for the whole time step. So this is a data set with a 15 minutes time step. So in this case, the value will be set constant for all the 15 minutes, and it is an average value, while the instval, which stands for instantaneous values, it's a single value for that exact instant, and then there is a linear interpolation between one value and the next one, as you can see from the green line. And the instval is the type most used for the flow record in a short period, and so it's better to have this type to do than other operation for the dataset. So in this first part, we have seen how we can screen and estimate some missing values to obtain a dataset which can be suitable for then other operation comparisons, and other operation can be done with other dataset, or how to obtain a dataset which can be used, for example, in other hydrological model or hydraulic model as an input. If everything is clear, we can move on to the part 2. Are there any questions? Okay, if there are no questions, we can go on with this presentation and start the part 2. For the part 2, we want to normalize the dataset because after this dataset have been screened, maybe they still require a conversion to a common time series scale before being used together in other computations. For example, for this exercise, in order to calculate an hourly reservoir inflow, the datasets for the lake levels and the outflows should be normalized to the same hourly interval because as you can see in this DSS file, we have the flow record, which has a time interval of 15 minutes. We have some elevation records, is free, which have different time interval. One is an irregular move. This one, the Jefferson Park at the Lake Winnebago, have a 30-minute time step, while this one have 1 hour. Then we have a record of precipitation with a irregular time step. And if we need to do some computation between elevation and flow and precipitation, we need to have the same interval. In this case, we are interested in an hourly interval. And so now with this part 2, we are going to change the time interval of every dataset into 1 hour. First of all, let's clear any time window. If you have a time window set, click on the bottom set time window and make sure is selected the no time window option. And apply this change. Then select the record for the Lutz Park Fox River. We use the fixed one and open the math function module. Okay, let's plot it and tabulate it. So this is the fixed one. If we tabulate it, it is clear that this dataset has a time step of 15 minutes with an offset of 3 minutes. So the first record is at 16:48 minutes. The second one is at 17:03, and so on with a time step of 15 minutes. We want to obtain an hourly flows averaged at the top of the hour. So we want to obtain a new dataset with a value at 17, 18, 19, and so on. To do this, there is a time function which lets you to do this change for the dataset. You have to select in time function, select the time function tab from the math function menu. From the operator menu, you have to select minimum, maximum over a period, and then the function time that will be useful to do this operation is the average over period. We want to obtain a new dataset with a period interval of 1 hour. So here from the menu, new period interval, we have to select 1 hour. Then We can leave the offset box unchecked because the default is to use the end of period. So essentially the average will be associated to the top of the hour. So we will have one value at 17, one value at 18, so at the top of the hour. If we click compute, the math function will be done and we can save as. This window automatically set the part E as 1 hour, which is the time step of this new calculated data set. We confirm the saving. Okay. Now one question can be, first let's tabulate the new one, the load spark records with 1 hour time step. Let's see the tabulated result. And what is the type of this resulting data? How does this affect the values computed for the new time interval? As you can see from the tabulating here, the new type is per hour. So at the beginning, we had some instant values. Now we have done an averaging over a period. So the new type is period average. And this means that the computed results, due to the fact that we are averaging the data over a period, and since the new value is an average value, we will not pick as high as the compared 15-minute data. So, for example, let's plot this one, the 1 hour time step with the 15 minutes. If we plot, we see that Watson, for example, here, the red one is the average. So maybe it's an average, so the highest values has been averaged, and we do not see anymore in the records because it's an average over 1 hour. So now we have the record of the flow with an hour time step. We want to, okay, we have already saved it. We want to fix also the two elevation dataset, which now do not have a 1 hour time step. So let's start with the irregular data series from du Lac, which is this one with the part E, irregular month. This is an irregular dataset because the dataset consists of reading taken at the top of each hour, as well as one taken every 4 hours at the satellite shoot time. So if you tabulate this dataset, as you can see, there is one value each hour at top of the hour, plus a value that comes from a satellite observation at the minute 17 or every 4 hours. So this one, and so on. One value every 4 hours. Now we just transform this into an hour time step dataset by selecting it, launch the math function module, and then from the time function we can select from the operator menu, irregular to regular. Okay, we select the interpolate option. This will interpolate the values in order to obtain a new dataset with the time interval that we specified. We want 1 hour time interval. So make sure that from the menu of the time interval you select 1 hour. Okay, and compute with this information. You can tabulate from here to see the difference, but first select from the display menu original data with computed. So when you tabulate, you will see the comparison. You see that now in the modified dataset, we do not have anymore a value at the -17. We only have one value each hour, which was what we want to obtain. And this is for all the record. Okay, so also this dataset has been fixed. Let's save. Yes. Okay, now we have this 1 hour time step dataset also for the Fond du Lac elevation. We still need to fix the Jefferson Park elevation. This dataset consists of instantaneous readings taken at 2 and 32 minutes past each hour. We can tabulate to show you. You see there is one value every 30 minutes, but with an offset of 2 minutes. So at 1702, 1732, and so on. If we simply convert this data set to an hourly interval, the levels at the top of the hour would be linearly interpolated between the values at 32 and 2 minutes. But in this way, the value will be attenuated at the high and low points. So in this case, it is preferable to avoid this attenuation, and we can extract the 2 minutes offset reading and snap them. You can do this from selecting the Jefferson Park elevation dataset, opening the map function menu. Okay. Again, with the time function tab, we can select irregular to regular as before, but in this case, we select the snap option. We set the time interval to 1 hour, which is the time step we want to obtain for all the dataset. And then we can check this option, the tolerance forward, and we can set a tolerance of 2 minutes. So in this case, this math function will transform our dataset from 30 minutes with the 2 minutes offset into a new dataset with 1 hour time step. But doing an offset of the time series with a 2 minute forward. So in this case, we are not going to lose any information, and we are going to keep the most high and low value present in the record. click compute, and save this new record. Okay. Let's select the original dataset and the new dataset calculated with the math function irregular to regular. So I select these two and tabulate. As you can see, we have a value every hour, but they are still reported as at the wrong time. But it's this is due to a bug in some of the version of DSS free. I don't know which version do you have. Maybe in yours the operation has been done correctly, but we can simply adjust this by doing a shift in time. So, for example, I select the 1 hour time step series. I open the math function. I go to time function tab. Then from the operator, there is the shift in time option that we have already seen in one of the previous exercise. And I can shift the whole data series by a constant amount of time. In this case, we want to shift all the dataset backwards. So we have to insert a negative value here in the box. So I put -2, and then I select minutes from the drawdown menu. If I compute a window, it say me that the time shift math function is going to overwrite on the original one, and I can choose to remove the original one or save the new computed one, save as with a different name. I can, in this case, select save as and specify in the part that this is the shifted one. So we can check if the math function of shifting time has been done correctly. Okay, save this one. So now let's select the two time series with 1 hour interval. This one and the shifted one. Let's plot. Yeah, maybe the plot is not clear because to me it's a very low value. Let's tabulate. Okay, from here is it clear that we have shifted of 2 minutes backward? The shifted one now has a value each hour at the top of the hour, which is exactly what we want to obtain. So now with this part 2, we obtain all the time series with 1 hour time step. So we have this flow record of Lutzpark with 1 hour time step. We have the Fond du Lac elevation with 1 hour time step. And we have also this Jefferson elevation dataset with 1 hour. This one, the shifted one, is the correct one. And you can see we have all these data series that now are corrected and can be used for some computational, some balancing, and other mathematical operation that can be done with this elevation and flow data. In the DSS file, you can find also the Jefferson Park elevation dataset fixed. So if the problem of the shifting is still remaining, and if you don't want to do the shift in time operation, there is still this one, which have been already fixed and have a value at the top of every hour. Do you have any question about this exercise?
Yes, Fritka, I think it is very interesting, but because of there is no opportunity to exercise it by their hand, maybe later, I encourage all of you later if you exercise these very interesting calculations and mass functions. Many of question will raise at that time, will be raised. So is it possible to raise their question within coming days if there is any question? Are you available, Federica and Giacomo?
Oh yes, sure. You can maybe emailing us with any question that you can have. Maybe after checking better and this exercise, we are available. Yes.
Good. Thank you so much.
Okay, so I think Federica maybe can recap what we have done until now, and then that maybe we have more time. We can do some other exercise, some other example of different things that might be interesting to see. So okay, maybe Federica, if you can just do a small recap of what we have seen today until now.
Okay, sure. So let's see, in the first day, we have seen a general overview of what is the HEC-DSS-Vue, how does this program works. You have learned how to catalog the files and how to search for records. You are also now able to select data, to put some filters and select order. We have seen also how to view the data, both in the plot format, in the tabulating format. We have seen also that there are many options about changing the characteristic of the plot, for example. You can personalize the graph, changing the lines, adding some legend, changing the name of the axis and the colors and many other options. We have seen that we can also plot and see only specific time of the whole record by setting a time window. And then we have seen also how to enter the data in different ways, from external file, from Excel file. Yeah, we have seen we cannot import automatically the data from an Excel file, but we can copy the values and insert new data set. Then yesterday you have done some exercise which summarized most of these things. So we have practiced about, for example, the different view, the path name view, the condensed view, and so you know how to manage and organize the data set and all the records. While today we have moved on a more different topic. We have seen how we can also modify and edit the data set we have in our DSS file. We have seen the most useful utilities, so how to duplicate the record, so how to create a copy of a single record or multiple record inside one DSS file. We have seen that we can delete the records, but also undelete them. We have seen that we can modify and rename some of the parts of each records. We can copy the records from one file to another one and also create a new one. And we have seen also how the merge command works. Then we have seen how we can export the data and by printing, copying, or exporting in other file. We have seen that we can print both a catalog list or we can print the graph, both in a PDF format or as an image. And also in this case, we can choose different format. Or we can copy the table containing all the values of a record, copy and maybe paste in another format, like the Excel one, the Word, or other format you would like to use. Then we have seen how to edit the data. There is many options to edit the data. Maybe if I open again the presentation, I can just show in a very quick way. Okay, from this one, we can edit the data directly from the tabulation window. Just selecting the allow editing command. And so in this way, you can just copy, cut, and paste some specific cells from the records, or you can cancel, modify manually the single cells, or you can insert new values. You can also insert or append new rows or delete some rows. You can have some fast mathematical operation like the sum of a selected cell or the sum of the entire column. Then there is another way to modify the records, which is the edit in Excel mode. Or in this way, if you select a record, one or more record, you can open the data set in an Excel file, do every kind of operation you would like to do at these records, and just saving the Excel file. All the changes will be applied also to the data set present in the DSS file. Or another way is to modify the dataset with a graphical editing. There is the graphical edit button, which allow you to see in this window the plot, the dataset, together with a table in the bottom part. And you can also in this way change manually some values, or otherwise makes an interpolation of the missing value, or draw some. This is the interpolation of missing values, for example. or you can, using this button, modify some single point or draw a curve to approximate a new data set. And evaluating with this plot if you want to accept or remove or change the modification you have done. And then we have seen the math function, which is a very useful tool in DSS-Vue. There are a lot of different operations that can be done with the math function. All the math functions are organized into 6 categories. We have seen some of them, the most useful and the more likely useful to use. We have seen, for example, the arithmetic functions. We have seen some example of this, which use most of the arithmetic operation that can be done. We have seen, for example, one exercise with the add, the subtract, and then the general function contains a lot of other operations like the units conversion, the time function. Instead, I've also there are a lot of options. We have seen some of them. In general, all these time functions let the user to change something of some of the characteristics of the time series about the time interval, the time period. So, for example, we have seen that with the minimum, maximum, average over a period, we can do an accumulation over a new time period. We can set the minimum, maximum for a period, which is a really useful operations. And then we have seen also the shift in time that we have used also in this last exercise, and the statistic function, which do some of statistic function. With the basic, you can see some useful statistical values or information which are computed automatically with this function, or the cyclic analysis, which is something more advanced, and you can obtain a lot of cyclic results about your data set. And these are the most useful math operation, but there are much more. And for each one, there is some parameters to insert in order to obtain the result you want.
Okay, so thank you, Federica. I will now share the screen to show you a small exercise that we haven't seen yesterday. It was actually on the part of the day 1 presentation. You find it in the presentation of day 1 exercise. It is called this part 2. It's about graphics capabilities. And to do this, we can open, I will open it with you. 1 second. The file that has been shared to you with you is in exercise day 1 in part 2. We can open the DSS file, the one present here, the sample.dss. Okay. It has been open. What we want to do in the exercise is to, let's say, to play with the graphical to the plot to change the visualization of our plot, changing the viewport, the style of the lines, and to change how it appears,
Yes.
depending on what you want to show and how do you want to make your result presented. So at first, for this exercise, we can we want to select 3 specific records.
Actually.
To do this,
Because
we can...
all they are going, they are important. So there is no... Oh, sorry.
Sorry. Yeah, we can go to path name. We want to select the records with date. So in column D, 1 January 2022. So we go to this part D. We select the 1 January, 20 to 2002. Okay. Sorry, was not this one, I guess. I want the data with, sorry, part A, Dewey Lake. Okay, let me think. There is something wrong here. Because I cannot see what's presented here. Okay, let me see if it's this, Dewey Lake. Okay, here we are. You have to select Dewey Lake in part B. And then here we are, the 6 record about Dewey Lake. And we want to select the one of elevation. So we can double click on the one of elevation, the one with flow, and the one with precipitation, this last one with precip inch. Okay, so now, sorry, now that we have selected this record, we plot it. We plotted the 3 records. They appear in this way. That's a little bit different from the one from the presentation. Mainly about the colors, I mean, to make the color appear differently from one parameter to the other, where we have to go to View and remove this tick on Use Style Lines, so that you can see a different color per each parameter. This was actually the question here in the presentation. How many viewports are on the plot? 3. These are our 3 viewports, 1 per each different parameter, because if you remember, if we plot the different parameters, they will appear in different views, in different viewports. So we reached also the color we wanted here for the presentation. In the elevation curve is automatically in blue, so it's correct. And also, sorry, this was wrong, the presentation. This is not the question about the elevation curve, but was flow. The flow curve, it's in green. Sorry, this was the precipitation curve, that's in green on the bottom. Then the next step is to do some reconfiguration of this plot layout, through which we can modify it in different ways. A first thing that we would like to do is to make an adjustment so that this precipitation curve on the bottom here is plotted in the top viewport instead of the bottom here. And to do this, we have to go to do edit menu and to plot properties. No, sorry, to configure plot layout here. And from here, we have to find the precipitation, that is this last one, the viewport relative to the precipitation. We have to select it and move it with this small arrow on the right, we will move it on the top because we want it on the top. We do it 2 times. We click on apply, and we see that's already shown on the top part of the plot of the presentation. So then the other thing we want to do is to keep the elevation curve and the flow curve in the same viewport instead of 2 different viewports. And how do you do that? We have to go always to this configure plot screen. And here we have to select the axis of, in this case, we can select the last left y-axis here, corresponding to the flow. And also here with the arrow, we move it up, the axis. We see here from the panel that it has gone under the other viewport, the viewport that if we select apply here, we see that what we see on the screen is just a viewport with the two parameters, elevation and flow, on the same graph. And also, as we wanted, here is written the elevation and flow should be plotted in the same viewport with elevation on the left. Here, elevation is already on the left, in the left axis, and the flow is on the right one. So we did this. And the next step, that's about some modification to the graph, is, for example, here that we would like to invert the axis of the precipitation curve of this green one. In order to reach the same result of this image on the presentation. So to reverse it, from this configure plot settings, we have to go to edit. So you have to select edit properties. Let me see where is it, which is the precipitation. Okay, 1 second. Here, since I still see the viewport on the bottom that was originally created for the 3 different viewports, it's better if I select OK and reopen it again in order to refresh this view. So I go on OK. I will go to edit configure plot. OK. Now we have our 2 viewports. But what we wanted to do now is actually about the inversion of this graph of precipitation. So to do that, we have to right-click, so not in the configure plot, to right-click. Okay, we press here the arrow. We have to click with the mouse to this arrow here. And we have to right-click in the axis here of a precipitation. There is this edit properties. And there is the possibility to reverse the axis here on the bottom. So we click, we tick it, we press apply. Yeah, it has been done. You see the precipitation has been, the axis of precipitation has been inverted. And then another thing that we would like to do, like we see here, is that to adjust the size of the viewports, such as that the top viewport, this one with the precipitation, is about, let's say, half of the size of the bottom with the other parameters of elevation and flow. And to do this, to change the size of each viewport, we need to go to edit again, configure a plot layout. And here, if you see at the right of each viewport, for example, the first one, that's the one with the precipitation. It's written 50%. That's the same that's written also in the viewport of the bottom with elevation and flow. That's again 50%. We can modify these numbers, and we can okay, we have to select from here edit. After selecting the viewport, we have to click on edit and set the viewport weights. And from here we can select which is the weight of each of the two viewports. We want it more or less, I mean, the one on the top that's smaller of the one on the bottom. We can have, for example, 25% in the one of the top, and the remaining 75 for the one of the in the bottom. Okay, we press apply. Okay, again here in this screen we have to apply again. Okay, again, and now we see what are the results of what we have done with the much larger viewport of these two parameters, elevation and flow, instead of precipitation. Then another thing we can do is to adjust the y-axis on the elevation curve in order to set a range, a specific range, and not the one by default given by the program. To do this, we have to right-click on the axis. We first select the arrow, right-click on the axis. We go to the edit properties. In edit properties, we can select which is the maximum and the minimum of the graph. In this case, for the maximum, we wanted, sorry, we have to untick 647, and for the minimum, we want 645, for example. We can apply. And the same can be done for the flow, that we want to change the axis from 0 to 2000. We go to edit properties. We change minimum and maximum. The maximum to 1000, it's okay. And the minimum to 0. Apply. And okay. So this is actually what we did here to modify this graph, and we reached what we see currently in the presentation. A few other things we can do is to modify the fill color of the precipitation, again from the edit properties. We can go here. It's possible to use the plot properties that we have seen yesterday to modify the colors. In this case, we can press the fill here. It's already we have our under curves style. In fill, we select above. We can select the light green color, and we can press on apply. Okay, we see that the fill green is applied here to the precipitation, and we could do the same to direct curve. For example, here we did some dotted line on the flow curve, and a thicker line blue of the precipitation. Okay, it's possible from here actually to save the template of this file of this plot in order to have the same template if I open again the plot. To do this, I have to go to File, Save Template. I can save it. I will put it here on my desktop. I call it template. Template save. Now, if I close it, if I close the plot and I plot again our curve, I see that I don't see already the modification I've done. But if from here I press on File and Apply Template, I can get the template I created before, this one. And now we see that the graph is already updated to our template we have done. Okay, this is some other small things that we could do to change our plot, to put some other elements that are basically if you go here to plot again, it's possible actually to add small images, to the plot, and it's also possible. Now maybe I don't show you, but it's well described in the presentation, just how to add a small image here to the plot, changing the legend block. You can put it on the right or on the left. And it's also possible to, as I wrote here, to save it as a default plot in order that each time you open a new plot, this image will appear in your plot. So it's an interesting function, and there are many interesting functions in this type of styles of plotting and standard that you can make to your graph in order to obtain what you actually need for your work or for your presentation at all. So okay, I think we are done also with this presentation of this small exercise that's already that is available with the other material. We finished our time and we have done. We are okay with all the presentation we did today. We covered quite many of the main function of the HEC-DSS. Few things remains out, but they are somehow more advanced things, but also not really used in the normal work, in some normal utilization of the program. So we have seen actually what we actually do, for example, in our company when we want to do some operation and storage of files and of materials in DSS. So yes, Mona, I think we are fine for the presentation of today. Then in the next so in the next weeks we will have so all the other presentations and trainings about the other software we have used in this project, HMS for hydrologic modeling, HEC-RAS for the hydraulic modeling, and also SWOT, and again HMS for the sediment transport, RESSIM for the management of the basin and the reservoirs, and actually next week there will be the training about QGIS for the managing of maps and visualization of different files and things that you will see next week. So I want to thank you all for attending these meetings, and I don't know if you, Mona, want to say something.
Yes, Giacomo and Federica, we really appreciate your efforts in conducting this module regarding HEC-DSS-Vue. And thank you, the participants, for your commitment and your patience to attend this module. I think it is very important session regarding the time series and database issues. We benefit a lot from this session. Thank you so much. And I'm sorry, from the first time we have to introduce ourselves to each other to know who are in the platform, but maybe the next time we will do that, and we will learn from all the technical challenges that we faced. So thank you so much, and see you soon. Looking forward to meeting you in the next QGIS session, training session. Thank you so much. And Dr. Zerhon, I saw your hand raised. So yes,
yeah, just this is just small reminder. Only few of participants completed the list or the form for day 2. So this is just to remind them to complete the form before leaving the meeting. Yeah, that's all I want to say. Thank you.
Thank you, Dr. Zerhon. Thank you, our instructors. Thank you, participants, and see you next week, inshallah.
Great. Thank you all. See you soon.
Thank you.
Thank you so much. Bye.